webinar series. And I believe we have Dr. Brewer on the line now. Roger, can you hear me now?
I can hear you. Can you hear me, Eric?
Yes, I can. All right, go right on ahead. Thank you. Ladies and gentlemen, we're going to be starting the webinar right now. Thank you.
Okay, sorry about that, folks. We'll get this down one day. Anyways, aloha, this is Roger Brewer with the Hawaii Department of Health. And 2 weeks ago, we went over the results of a discrete sampling field study we did to look at the variability of discrete samples around co-located grid points. What I want to talk about today is actually the more fun part, the implications for environmental investigations. So, there are a lot of things we could go over today, and we are going to go over a lot, but I'm just going to spend a short amount of time on each one of them. Quick acknowledgements, too many people to count. Really, all the notes here today, a lot of people joining in today, I think will recognize some of the points that we bring up. We've been discussing them for years. And this is basically a compilation of what we've talked about over the past several years. And we're still thinking about this. So there's a lot more to come. Quick references. The title of the field study itself, report small-scale variability of discrete soil sampling data. Last update was June 2015. Today we're going to talk about part 2, causes and investigations, causes and implications for use in environmental investigations. We'll probably update part 2 next year based in part on feedback we get from the current one. And it's posted on our What's New section of our webpage. Also, all the data are available in Excel format, so any of the statisticians out there love to play with data and go for it. One thing we're talking about today, this comes up a lot at workshops we give, is multi-increment sampling and sampling theory and decision. It's just another tool in the toolbox, or is it something much more than that? It's actually the latter. We haven't really done a good job of explaining that. This field study gave us the basis to do that. So we'll talk about that again at the end. Now, when we give workshops, it's invariably the people who are just getting started in environmental work, they ask, why you go on and on and on about discrete samples and potential limitations and error and such. We get it. Why do you keep going over this? But it's important to remember that for people just getting started, people like me, that we grew up essentially with discrete soil sampling. That's the way we were trained for 10, 20, 30 years even. So it's a big deal to make this switch and to think, well, maybe what we were doing in the past wasn't as accurate as we thought it was. It's as big a deal as when people started realizing the world was round instead of flat. You can do a lot of things assuming the world is flat, but try flying a satellite or putting up something like that. That's when you realize that we're sailing around the Earth. That maybe your initial conclusions weren't necessarily correct. So Thomas Paine put this succinctly. I won't reread that 200 years ago in the American Revolution. Quick review of the data that we went over 2 weeks ago. Again, this is on the web. We actually, the whole point of this field study was very simple. We looked at the origins of discrete sampling methods and grid sampling. How did this come up in the first place? Here's some quotes from some of the early guidances on soil investigations in the 1980s. So from the EPA's 1985 guidance verification of PCB spill cleanup, which really led the way in this. The implicit assumption that contamination is likely to be uniformly present anywhere within the sampling area is reasonable, or they're saying it's the same concentration anywhere within the spill area. The PCB level is assumed to be uniform within the contaminated zone, spill area, sampling area. They call it different things, and 0 outside of it. The 1989 EPA document, Methods for Evaluating the Attainment of Cleanup Standards, it's the basis for a lot of risk assessment guidance. When there is little distance between points as expected, there will be little variability between points. These are key assumptions that have never actually been tested thoroughly in the field outside of some of the Army Corps' work for munitions. So this is what we set up then. It was the quick, simple study question: how variable are contaminant concentrations in co-located discrete soil samples around a single grid point? So we went to 3 different sites. I'll show you in a minute. At each grid point, we did 2 things. First, we collected a sample from the middle of the grid point, and we tested it 10 times and looked at the variability of the contaminant concentrations. And we call this intra-sample variability. For the metal sites, we used a portable XRF in a lab setting to test the sample 10 times. For PCBs, we actually took the sample as undisturbed as possible and split it up into 10 jars and had the lab test every jar. So that was intra-sample variability. Second thing we did was take 5 samples around that grid point again, and when we processed these using multi-increment sampling methods, so sieved, dried, and subsampled, and had those tested for the same chemicals. So we call this inter-sample variability. And this, the data we get back from the lab, we assume is representative of the sample that we sent to them. Here's the 3 different sites we looked at. There was a study site A was arsenic contaminated soil from wastewater, which we assumed, we knew from discrete sample data, there wasn't that much variability over short distances. Study site B, lead contaminated, was lead and incinerator ash mixed with fill material. And we knew, again, from discrete data, we start seeing more variability. Study site C was a PCB contaminated soil from transformer oil. And here the numbers were all over the place. We knew from, again, from discrete samples. So we had a nice range of expected variability. Each one of these sites, we set up 24 grid points and collected the surface samples, as I showed you there, average 0 to 4 inches, tested the variability within and between samples. We also collected triplicate multi-increment samples at these 3 sites, and I'll show you that data later. But here's what we found. Here's the arsenic site. This is just a box graph, arsenic concentration at each one of those 24 grid points. Just our estimate of the variability of discrete samples around that individual grid point. So on average, it actually wasn't that much. On average, we saw about a 2-fold variability of concentration of arsenic in any given discrete sample collected around a grid point. And again, we're looking at a combination of inter and intra-sample variability. Maximum variability we saw around a grid point was only about 4-fold. Now, I say only 4-fold could be a big deal if you're doing risk assessment or comparing numbers to screening levels and such, but this is actually a fairly uniform site, if you want to call it that. Here's the lead site, and here, the variability around individual grid point started pushing 10-fold. So this is really interesting for this site because most of the data and most of the sites or the grid points we looked at, we could find a discrete sample around one of those grid points, both above and below our office's screening level for lead in soil of 200 milligrams per kilogram. And actually, the variability was so much we saw the same span across EPA's residential screening level for lead, 400 milligrams per kilogram. So again, any given grid point, we could test discrete samples around that grid point and find this much variability around it. Start thinking of implications for those. This site was kind of like a house salad. Any given handful, you'd see a lot of variability within a handful, but you go to another point within the site, it was kind of the same salad. You'd see some differences, but it was similar range of concentrations. Maximum difference we saw around a grid point, about 40-fold. We only tested a small amount of the soil around a grid point. If we kept testing thousands of discrete samples, whatever, we'd see more than this. It gives you an idea. So again, at this site, any given grid point, you could find a concentration of lead in a discrete sample above or below your screening level. And this is where you really end up chasing your tail when you're trying to map through a site like this using discrete samples. Here's what we saw at the PCB site. Notice that on the left-hand scale, I had to switch to log scale on the left-hand axis. So here, the median variability we saw between the maximum concentration of PCBs in a discrete sample and the minimum concentration of PCBs in a discrete sample, about 40-fold. This really starts to make a difference. Key point here, we saw the same variability whether we were in low concentration areas of the site or high concentration areas of the site. So anywhere you test on the site, low or high concentration, you see a lot of variability. We had one grid point where we saw over 1,000-fold difference between the maximum concentration of a discrete sample and the minimum concentration around that point we estimated. So this interesting thing with the PCB site, something's going on there. This is where we started coming up with an idea of looking for nuggets in the soil. And here's a true hotspot at study site C in the PCB site. Here we collected, you see our 5 process samples around this grid point. The average range of PCBs, 4.9 ppm up to 91 ppm. That's big enough in itself. The sample that we tested for intra-sample variability, that 6th sample there, the average was 2,400 ppm. So that was a true hotspot. So you see how much variability you can see around one of these. Really, the concentration you get for a discrete sample around a grid point is totally random within a range of possibilities for that site, for that particular grid point. Here's what was going on at the PCB site, and actually all these sites. It's just a nugget effect. That's one of the main causes of variability over short distances, or even within a single sample. At study site A, the arsenic site, a consultant here, Bill Cutler, did his dissertation on that whole area. And there's small nuggets of iron hydroxides in the soil that are infused with the arsenics. When they sprayed the arsenic on the ground, it would absorb into the iron, and you get these arsenic-infused nuggets. You can get super high concentrations if you happen to get one of those in your sample. Study site B, this one we already knew there were small, tiny pockets the size of a marble or something of lead concentrated ash within the fill material. If you happen to test one of these as a discrete sample, you get high concentrations of lead. If you didn't happen to have one of these in that aliquot tested by the lab, you get much lower concentrations of lead. Study site C, we looked at the soil under a microscope. You can actually find these tiny PCB-infused tar balls, at least that's what we think is going on, where the droplets of oil sank into the soil and then form small tar balls. If you happen to get one of these little nuggets in the aliquot subsample tested by the lab, you get screaming high levels of PCBs. If you don't, you get low levels of PCBs. So that one thing to point out here is there's a hang up on looking for the maximum concentration of a contaminant in soil. But if it's there, there's only two choices. If it's not there, it's 0%. If it is there, it's 100%. For the PCB site, if we could go in with an electron microprobe or something on one of these little PCB-infused tar balls and hit the matrix, at some point we'd be able to test a small enough mass, in theory, to find 100% PCBs. So that's one take-home point here. Looking for maximum concentrations of contaminants in soil with discrete samples is really kind of a myth. It depends on the volume and the mass of soil you're testing. So the whole bottom point with that, the bottom line is discrete samples are just too small to capture and represent small-scale variability in soil. We talked about this a lot. 1980s, we thought soil looked like a bowl of Cheerios. Any single sample or subsample mass, no matter how small, you get the same concentration. 2010s now, reality is that contaminated soil is more like a bowl of Fruit Loops. So any particular grain you test or subsample you test could be significantly different from the one just adjacent to it. This is what soil contamination would probably look like if you could see it. Jackson Pollock's painting here with splatter painting. Move that red dot around, you see much different, a huge difference in concentrations of the gray matter, whatever they may happen to be. Here's on the right, it's a picture of spilled milk. So imagine trying to test this site if you couldn't see it, say it was PCB oil or something, with discrete samples. You'd find it here, not find it there. Maybe you think you know what's going on at the site, but in reality, you don't have a really clear idea. And the problem can't really be fixed by collecting more discrete samples. That was the conclusion of the first study, and we'll look at that in a lot more detail in this webinar. Because the problem is the variability in very tiny masses is so great that it's really random, the concentration you get reported from the lab. And we're just testing samples that are much too small. This is why confirmation samples often fail. And again, statistics can't fit bad data. So that's statisticians get dumped on with really bad data sets a lot of times and asked to make decisions based on it. And that's always been a problem. And it's not the statistics' fault. It's more how the samples were collected. So update to original assumptions, the implicit assumption that contamination is likely to be uniformly present within a sampling area, now we know is not reasonable. We know that in the case of PCBs, the PCB level cannot be assumed to be uniform within a contaminated zone spill area, whatever they call it, a different guidance, and zero outside of it. Then for the 1989 document, when there is little distance between points, it's expected that there will be significant variability between points. That's really what you have to start assuming now. So what are the implications for this? And we kind of followed the Matrix theme. It's one of my favorite movies. There's Neo taking the red pill, which is when you go down the rabbit hole into Wonderland and see really what the implications are for this new information that you're getting. So that's what we're going to do now. We've all taken the red pill by joining in. So let's go down the rabbit hole and see what's going on. It's part two. I've got a lot of outlines in here to keep myself organized. First, we're going to look at representatives of laboratory data. What does that number you get back from the lab really mean? Then we're going to look at potential errors and mistakes in mapping the extent of contamination with discrete samples. And one of my favorite subjects, we're going to go to isoconcentration maps and look at hot spots. And when are they real? Sometimes they are, and when are they not real? And then we'll look at risk assessments, which I'm really just starting to think about with some other people. We need to think about it more. How do we know these exposure area concentrations we get are actually accurate or representative. How do we know the data set is representative to start with? Then we'll spend just a few slides on sampling theory and DUMIS investigations, and then we'll end up talking about regulatory hurdles, and especially TSCA. That's one that a lot of us have been having fun with recently. And that was one of the motivations for actually doing this field study. So representatives of laboratory data, that's pretty easy. If you look back at SW 846, it's kind of the Bible of testing samples. In the details in Chapter 3 for soil samples, it says mixing should be performed as needed or feasible to homogenize the sample until the subsampling variance is less than the data quality objectives. Well, that's a nice thought. Nobody does this in reality. There's no standard laboratory protocol for homogenizing soil samples. As one chemist from a lab told me a few weeks ago, try doing that in a jar. What happens is all the fines settle down to the bottom, which is where a lot of the contamination might be. And it's really impossible to pick out a representative subsample just from a jar, even if you try to mix it mechanically. So that's the key point. Bulk soil samples can't be efficiently homogenized really without grinding. And even grinding, you have to be careful in subsampling. So a single random 1 to 30 gram subsample taken from your sample you sent to the lab, it's unlikely to be representative of the sample that you submitted in general. If you could actually test that entire sample you sent to the lab and extract it, which you can. So laboratory processing and subsampling is critical. And under multi-increment sampling methods, with according to sampling theory, you air dry the sample, sieve it. You know, for VOCs, you preserve the sample in methanol. But for the air dried samples, then you collect 30 to 50 increments from that spread out air dried and sieved sample to prepare a subsample for analysis. This preserves the field representativeness of the original bulk sample. So the data you get back from the lab now, you can at least say what's probably representative of the sample you sent. You can do laboratory replicates where they subsample it multiple times and test individual or compare the data from individual subsamples. And that's where, again, you're testing the data quality. The labs have been calling to do this, recommending to do this for decades, but it really hasn't been pushed by regulators. Plus, it's an added cost. And plus, we don't really know what we were looking for before. So did it matter if you didn't process the sample or not? So that's laboratory stuff. That's pretty easy. ITRC, ISM webinars do a really good job of covering laboratory processing. Let's look at the fun part now, mapping the extent of contamination. And first we'll look at the effects of randomness and discrete data. One thing to point out, my background's actually a geologist, but I was trained in risk assessment early on. So I've always had kind of a schizophrenic relationship between field data and analyzing the field data. We'll talk about that more later. Here's in an ideal world, just a real simplistic example here. Here's a site. We've collected 3 samples across the site. And the upper part of the site, our discrete sample came out yellow. Let's just say it's low concentration. In the middle of the site, our discrete sample came back orange, higher concentration. The bottom part of the site looks like a hot area. The concentration we got in the discrete sample was really high. So what we're assuming here is that when we send a laboratory, first that our sample we collect in the field is representative of the surrounding area. And also when we give the sample to the laboratory, we're assuming the laboratory can test any given subsample or small mass of that soil, and it's going to be representative of the sample in general. Well, this is what you hope is happening. Here's what's really happening in a lot of cases, is that discrete soil sample is very heterogeneous within the sample itself, and it's probably not representative of the area around it. Maybe it is, maybe it isn't. So when you give a sample to the lab and they're randomly testing an aliquot out of it, then that's completely random within a range for that subsample. In this example here, all the discrete soil samples could be exactly the same, but because of the heterogeneity, when the lab tests a small mass of those samples, they get different numbers. So it's kind of like a salad. Think if you had 3 salad bowls side by side, all exactly the same, and you randomly pick something out of the salad to test with a pair of chopsticks. You can get completely different numbers for each one of those bowls of salad, even though they're exactly the same. This is what causes a lot of confusion in the field with failed subsamples or confirmation samples. And we'll look again at that data. So really discrete samples that you get, if you're not careful, they're just random specimens of field heterogeneity. They're not really a true sample of what's going on in that area. The same thing with laboratory data. It's a random specimen of sample heterogeneity. And whether that's useful or not, maybe it is, sometimes maybe not. This isn't a new discovery. Here's some quotes from earlier EPA guidance documents that some people sent me to look at. These are really interesting. What were they thinking about in the 80s? So they knew a lot. They just didn't understand. They didn't really have an alternative to do something different. So 1989 soil sampling quality data, user's guide. Soil is a very heterogeneous material. Samples with very small support volume, like the mass tested by laboratories, just a few grams, may vary from 0 to very high concentrations. So they knew all this. The second one, the so-called grab sample or discrete sample, was not really a sample, but a specimen of the material that may or may not be representative of the sampling unit, which now we would call a decision unit. Great care must be exercised when interpreting the meaning of these samples. So the people that wrote this guidance, they were thinking about these things 30 years ago. So let's look at some examples of mapping errors, but still using this discrete sampling approach. Here's an example I put together, hypothetical. Here's a commercial site. Let's just assume we want to know where the hot spots or contaminated soil is within the main part of the commercial site. Let's just assume for this example that the boundaries we know are clean for some reason. So we go out and collect 6 discrete samples and we get an interesting pattern. And humans are really programmed to look for patterns. Here, so we find some contamination, go collect another 6 samples. So we found a little bit more. It looks like there's more contamination to the left side, maybe not, and we get this kind of odd, isolated hot spot sitting up in the middle right. So we go collect some more samples to the end of it. And again, we get these little isolated spots of contamination, which we think maybe they contaminated the soil. They spilled something over here or over there, and most of the spillage and contamination is on the left-hand side. Well, that's kind of right. And here's what I use to generate this map. I know this is kind of confusing, but you can look at it later. Really, this just shows the degree of heterogeneity for discrete samples within each one of these areas can be really huge. So when you're getting these green spots or clean samples on the left-hand side of this map, it could be just completely random. If you move that sample over a few inches, you might hit a red spot. It just shows you how you can get really confused with discrete sample data. If you excavated those initial areas, then you're still probably going to leave a lot of contaminated soil behind, as we show in this map. Then you're going to necessarily dig up these sample size hot spots on the right-hand side of the map, where the mean concentration is really what we look at for that area in general would pass our screening levels. So that's the key point, is encountering false negatives and false positives using discrete samples is unavoidable in a site investigation. You're eventually going to hit a point where the variability of the contaminant concentrations at the scale of a discrete sample is going to overlap your screening level, and you're going to start to get really confused on what's going on. Here's an example, real-life example of pesticide mixing area, contaminated dioxins and arsenic. I had a lot of discrete data for this site. The perimeter, we don't show all the points, actually had 100 discrete samples that someone else tested to verify what we were doing. It looks like a nice map. It's a nice pattern. It kind of matches what we think was going on in the field. Well, we went back to the site and did multi-increment sampling, and that whole interior was contaminated, whereas skipping back, the discrete samples suggested that there were large parts of the interior area that were clean. Multi-increment samples, we collected lots of increments within these blocks and tested them as one sample, showed the whole area is contaminated. One interesting thing here is that the bottom left, you see these 2 little orange boxes. These were outside the gate of the mixing area where the trucks were going in and out. There were a bunch of discrete samples went through this area and declared it clean. When we did multi-increment sampling, much larger samples and such, when we identified pretty clearly these areas were heavily contaminated, they had to be included in remediation. So that's the key point. For this site, the lateral and the vertical extent of contamination was way underestimated by the discrete samples. Here's another example. This is from previous example 2 is using ITRC's ISM webinars. Here's another one from their webinar against a site from Hawaii. This one was PCBs. Well, we had what we thought at the time, 10 years ago, lots of discrete samples here, had a good idea where the contamination was, we thought, based on the discrete samples. Went back, but keep in mind now, the lab's only testing a spoonful of dirt at each one of these spots. They're not really as big as a car, as I put on this map. It's kind of misleading. Here's what we found with multi-increment samples at the site. That whole left-hand area of the property was heavily contaminated with PCBs. The discrete samples completely missed it. And again, here's discrete samples, multi-increment samples, at least 2 or 3 times more contamination than we initially anticipated. The ironic thing here is, as we collected more samples, we went back and did more detailed multi-increment sampling investigations. We started finding higher concentrations of PCBs, eventually over 50 ppm, which you're going to do if you start collecting really big samples, including those nuggets and what the lab tests. So a quick update on this. The we found a lot more contamination at the site since then. Because the concentrations exceeded 50 ppm, it threw us into TSCA. And we're currently doing additional work at this site. And under TSCA, following discrete sample protocols, it would require almost 1,000 discrete samples to be collected at this site to map out the PCB contamination. We've been having discussions with US EPA scientists for a couple of years about this, and they're well aware of the problems and such. Right now, it's mostly a regulatory hurdle, but we're trying to work with the EPA. We are working with EPA scientists and attorneys to develop a regulatory pathway forward using the risk-based option. We'll look at this again toward the end of the presentation. Here's a great quote someone sent me: the best way to get rid of a bad law, I won't say bad, but an outdated law or policy repealed, is to enforce it strictly. That's from Abraham Lincoln. Okay, so again, looking at the interpretation of ISA concentration maps, let's look at heterogeneity and artificial hotspots. This is something that's always comes up at sites. You find these hotspots with discrete sample data. What do they really mean? We talked about it before. We'll look at it in more detail. One thing I'll point out here again, like these previous sites, the parties associated with these sites, the RPs, US EPA, HDOH, and the consultants, we're all well aware of the problems that are going on. And we're just using these as examples. Here's something I always wonder, back to that lead site. What would that site look like if you collected a single set of discrete soil samples? What would this look like on a map? So think about this. At any given grid point, you can find a concentration above or below our action level. Well, here's some examples we did. We actually programmed this into an Excel. I didn't know you could even do this. Someone showed me how to do it. So at each one of these grid points, just looking at we estimated a range of lead concentrations at each one of the grid points based on our discrete sample field study. So we would go through and have the Excel randomly pick a concentration within that range for each one of the grid points. Here's the first example. So watch that upper left-hand grid point. Excel picked a random concentration of 165 ppm. And we knew at grid point 21, the range we estimated for lead in any given discrete sample was 103 to 419 ppm. So here's a map we get. We do that at every single grid point. We get this nice pattern of kind of hot areas over here, isolated hot spots, and a hot area down here. But then we had Excel go back and reselect lead concentration for each one of these grid points, again within that general range. Here's what we get: a completely different pattern. So for grid point 21, within that range, 103 to 419, Excel, first time it picked 165 ppm. Next time, just randomly, it picks 401 ppm. All of a sudden, it throws us up into a red zone, heavily contaminated area. So you see kind of general patterns, but you notice the hot spots shift around. They shift places. So you get these bouncing artificial hot spots. They're just artifacts of small-scale heterogeneity. And we did it again. We ran through this lots of times. And you see the third example here. Now you get a big pattern of lead contamination in the upper part of this site. And again, it's total artifact of small-scale heterogeneity. You see the fourth time we ran through this, Excel again picked completely different concentrations for each one of the grid points. There's the pattern generated. And we kept doing this. And if you stand back and look at it, the patterns look similar, but when you zoom in close, you can see the hot spots are bouncing around and such. So it's really isolated hot spots or even fairly large hot areas based on discrete samples. You can't really trust them. They could be just an artifact of small-scale heterogeneity or distributional heterogeneity at the scale of a discrete sample. You can do the same thing with a deck of cards. Each one of these 24 grid points, just put a deck of cards and randomly pick a card from that deck. We'll make aces purple, face cards red, 7s to 10s yellow, and then 2 to 6s green. And just randomly pick a card and look at what kind of patterns come up. Well, we know the average, the mean concentration, we'll call it that, at every single grid point is exactly the same. It's the same deck of cards, but look how the patterns change. Here's the first time we randomly picked a card for the grid points. Now we go back and do it again, pick a new set of cards, we get a new pattern. And again, similar, but the hot spots, the face cards are bouncing around along with the aces. Do it again, another pattern, do it again and again and again. You get lots of different patterns. So these are completely random artificial patterns that are completely an artifact of how we're collecting samples at a site. But imagine if you only did this once, you could easily get fooled by the patterns that are generated by discrete sample data. So again, something to think about in more detail. You can have fun with this at home. This is what happens at the PCB side also. Now, large-scale patterns can be real. So here's our 8 iterations of this, randomly selecting a PCB concentration to each grid point within the range that we identified for that grid point. You can see the upper part of the site consistently is more heavily contaminated than the lower third of the site. This is a real pattern. We know this at the site. But within this area, you can see your hot spots are bouncing around. So you can't really trust the data around any given grids point. We'll look at that site again later also. So think about that. Now let's look at some example over-interpretations of discrete data for isoconcentration maps, which I've been guilty of doing for decades. But it's interesting to think about in more detail. Here's a really fun map that was just published a couple of years ago. USGS went out and collected around 4,000 essentially discrete soil samples across the U.S. in areas not assumed not to be contaminated by any anthropogenic sources. At each one of these dots on the map, they went to a 1 square meter area, collected soil from 9 points, a big sample, 1 to 2 kilograms, which is great size. Then they ground it and had it subsample and tested. So they got really good data for each point. Here's the map they generated. So these large scale patterns you see here are real, and they're actually tied to geology. We'll look at in a second. But we're going to zoom in and look closer at these small scale patterns you see with these samples and think about where they're real or not. First, we'll go to Oklahoma and then to North Carolina. But look at the large scale patterns here now. And for the geologists in the audience, here's a geologic map of the U.S. And you can see the large scale patterns of arsenic in surface soil. That was arsenic. I forgot to mention that. They match up fairly well with regional geologic trends and different types of rock. So the large scale patterns are real. How about the smaller scale patterns? We're zooming into Oklahoma now, if you can see it barely outlined here. So it's about a 400,000 square kilometer area. Here they've got about 300 these really good discrete samples where they were processed, subsampled and such. So these large scale patterns here, they're probably real. They're probably related to just geologic patterns or whatever soil patterns in the area. But the resolution you see within these large scale patterns is best we can say is they're a complete artifact. They just telling you something about the interior distributional heterogeneity of arsenic concentrations within these large areas. Any one of those given points or red spots are not really real. If you went back there and shifted your sample over a foot or two, you might get a completely different number. And we talked about this with the USGS. They wanted to leave this in there because that was their whole point. They wanted the maps illustrate small scale heterogeneity within large scale mappable areas, but you can't trust that small scale heterogeneity. Here's, like I said last time in our meeting, we go to my sister's area. Let's jump back real quick. In North Carolina, you see that over on the right, see that one hot spot there? I looked at that and said, that's where my sister lives. It's a hot spot of arsenic, one of the highest concentrations they found in the US there. So let's look at that in more closely. Here's that spot just zoomed in. Again, this whole spot is based on a single discrete soil sample. It was really good. It's a good sample, ground and such, but it only covers 1 square meter. But using the computer program, the isoconcentration program, expanded that hot spot to a 2,400 square kilometer area that happened to include my sister's house. I also did my undergraduate geology work here. I know this area very well. It's all metamorphic terrain, very heterogeneous. It's a melange, if you know that term. There are a lot of mineralized zones here. So on this one sample here, they probably just happened to hit a very narrow mineralized zone that had higher arsenic in it. There are actually some small mines in here, but a vein, maybe a few tens or maybe a few hundred feet wide at most, but definitely not something you could expand over 2,400 square kilometers. So these are all false hot spots that you can get. They're just artifacts of small scale heterogeneity. Here's a more realistic map of the US data for arsenic and surface soils, which I tried again to put in their report. They didn't want to. So it's not as pretty a map as their original one. This is about the best resolution you can give with their map. You have these large areas, higher concentration here, lower concentration there. That's about all you can say. If you look in their report, if you look at the end, they did put this in as clarifying, is that the resulting data sets are not appropriate for accurate estimation of concentration really at any given point within the US. That's in the small print in the back. We see that at environmental sites that we do investigations at also. This is a great study, again, done by Bill Cutler, the guy who did his PhD on arsenic in Hawaii. At this site, it's a former pesticide mixing area, 9 acres. You can see the photograph here, that red circle. We knew they were mixing pesticides here in the 1920s based on arsenic. So we anticipate a lot of arsenic contamination. We actually went out to this site and did some small decision units with multi-increment sampling, and they all came out super hot. And it was going to take us a while to narrow down where the contamination was. So the consultant went out with a field XRF and collected 90 discrete samples. He actually took them back to a lab and tested each one and did a good job of mapping out large-scale patterns across the site. But again, in this upper zone here, you see a lot of heavy contamination. It's all above the action level. And then you start seeing these isolated hotspots again. So that tells you something's going on, finding concentrations above and below the screening level. Then the bottom area is pretty clean. So we see those three zones again. You see a zone A here where your heterogeneity range is still very heterogeneous, but it's all above the screening level. So discrete samples you can't miss because it's also heavily contaminated. You see this middle zone, which I'm just calling zone B, where you start picking up these isolated hot spots above and below your screening levels, cold spots and hot spots. This is where the heterogeneity at the scale of a discrete sample is starting to overlap your screening level. Then you get the lower area, zone C, where the heterogeneity range is below your screening level consistently. It's still heterogeneous. You might even find a few spots in here where discrete samples above our screening level, a 1 or 10 gram sample, but it doesn't really mean anything from a risk standpoint. The average is still below our screening level. We always look at the mean, which we're going to look at in a minute. So you get these three. So here's a realistic interpretation of discrete sample data there, where you identify these three zones. A is heavily contaminated. They're actually probably going to go ahead and dig this out before they collect multi-increment confirmation samples. B, you don't really know. It's up and down, above and below your screening level at the scale of a discrete sample. You really don't know if it would fail overall. The mean would in a risk assessment. You have to go back and resample that using multi-increment samples to be sure. C, probably no contamination down here. But again, you want to confirm it. This site, they're going to put in a bunch of residential homes, so you want really good data. You get the same confusion at depth. We looked at maps, but in subsurface, we see the exact same thing. I kind of mentioned at these other sites. But imagine putting a bunch of borings across the site. In this example, we got 9 borings in. The red is below some screening level. Green is below some screening level. So you start to pick out these kind of large-scale patterns of heavy contamination. They probably match your field data. That's a key point with discrete samples. You're usually going to catch the core contamination. It's when you get in these mixed areas that you're going to get confused. And again, you see these isolated hot spots. Of course, I just made this up, but this is what you would see. And you're wondering, why do you have a contamination down here at depth and nothing above it? Try to figure that out. It's all probably, in this example, it's just due to small scale heterogeneity. But remember, at each one of these points, they're big points on a map, but they just represent a spoonful of soil that was tested by a lab. Well, here's what this looks like in reality. And this will probably blow you away if you're not a structural geologist, but think about this in more general. Here's the small scale variability you'd see at the scale of a discrete sample within these zones. Again, these three zones: A, heavily contaminated, hard to miss the contamination; zone B, where it's really mixed at the scale of a discrete sample, above and below and such. You really can't get a good idea what's going on here with discrete samples. And then zone C, where you're getting isolated little hot spots, but in reality, they don't really mean anything from a risk standpoint. So if you excavated this based on discrete samples, again, you see this zone B especially, you're going to be leaving a lot of contamination behind, or some contamination. It may or may not be a problem. You won't really know that unless you collect your good multi-increment or incremental samples. So that was fun with hotspots. The next thing was look at risk assessments. And again, like I said, my background is mixed geologist, but I've been doing risk assessment work for a long time also. A big issue we've been battling with for years is comparison of data to screening levels. So let's look at that real quick. So this is the first red flag. It's when you're comparing risk-based screening levels, like our office's environmental action levels, US EPA regional screening levels, to individual discrete samples. Well, risk-based screening levels do not apply to individual discrete samples. That was the first flag in using them to map out contamination at a site. Maybe from a very qualitative, very screening level, but that's really not what the screening levels are intended for. Back to EPA's 1989 guidance, method for evaluating attainment of cleanup standards. The concentration in the intake equation that's used to generate the EPA's RSLs is the arithmetic average of the concentration that is contacted over the exposure period, or within your exposure areas. We're looking for means of exposure areas. And restated this in 1992. It's a classic risk assessment guide from EPA, calculating the concentration term. For Superfund assessments, the concentration term in the intake equation, again used to generate the RSLs, is an estimate of the arithmetic average concentration based on the set of sampling results that would be for an exposure area. So you're always looking for the mean concentration at a site. And the idea is you estimate the mean concentration for an area in the field, you compare that to the screening levels. You don't compare the individual discrete samples. This is restated just multiple times in the early guidance. Here's another one, 1989 risk assessment guidance for Superfund. Risk estimates developed for a particular exposure area. This is where we start getting to the idea of decision units, exposure areas versus single points. The mean concentration should be less than the cleanup standard, and the area of contaminated soil should not be larger than a specified size, i.e. the target exposure area. So again, the area of contaminated soil within your exposure area should exceed your cleanup level. Here's where we get hung up with maximum concentrations. Although this concentration does not reflect the maximum concentration that could be contacted at any one time, which ultimately could be 100% depending on how much soil you're ingesting, it is regarded as a reasonable estimate of the concentration likely to be contacted over time. So again, we shouldn't be looking for maximum concentrations of contaminants in soil. They're just an artifact of the mass that the laboratory happened to be testing. And it would be completely random. If you test a different volume of soil, you're going to get a different concentration. If you test a small enough mass of soil, eventually you'll find 100% of the chemical. So that's it. That was a big dilemma for me. I was actually, if you have to blame anyone for this, we're not really blaming anything. It's just odd that I was doing risk assessment and field mapping when I was consulting. And for risk assessment, I was insisting on at least 20 or 30 samples to make a call. But field mapping, then I was making calls based on 1 or 2 or 3 discrete samples saying, well, this area is clean. So I really didn't have an alternative, put it that way. Hadn't thought about it. I don't know why I was doing that. Should have thought about this 20 years ago. But when you're doing field mapping, then small numbers of discrete soil samples are routinely used to define the edges of contamination. That's what we've been doing. They're unlikely to be representative of the true contaminant means in those areas. It's something we know now. They can result in over or underestimation of contamination above levels of concern. So how many samples do you need to represent an area to get a good mean? Well, back in 1992, they looked at a lot of the Superfund sites that have already been studied. One thing they point out real quickly is, in the quote below, sampling data from Superfund sites has shown that data sets with fewer than 10 samples per exposure area provide poor estimates of the mean concentration. So you really, even from a discrete sampling standpoint, in a relatively uniform area, you need at least 10 samples to make a call on whether an area is clean or contaminated. Just a side thought here, I was thinking about the evolution of environmental data. We mentioned in the first webinar that the mining companies, mineral exploration companies, and agriculture, farmers have been using incremental sampling methods for decades. Maybe they were using individual discrete samples back in the 1950s, but they pretty quickly switched. If nothing else, they were doing a statistical analysis of discrete data sets. I'm assuming in the 1960s, 80s, still having lots of problems in the field, especially with mineral exploration. You don't want to invest $100 million in a new gold mining operation and then start mining gold and find out that nothing's there or not enough there to make the site economic. Your data or sample data were wrong. They started switching to multi-increment sampling methods in the 1980s pretty quickly. And now I can't imagine any geologists working for a mineral exploration company collecting discrete samples. They would never do that. They get put out of business very quickly. Here's something interesting. The Environmental Risk Assessment Group in the mid-1980s or before, I say they were looking at individual discrete samples. I bet a lot of them were thinking about statistical analysis then. That's why they reviewed the EPA's Superfund database. By the late 1980s, they were already publishing guidance. EPA was, the statisticians, the risk assessors saying, hey, wait a minute, you need to collect lots of discrete samples. You need to do a statistical analysis, estimate means. You can't really rely on single individual discrete samples. And now in the 2000s, we're switching slowly over to multi-increment sampling methods to get even better data. The field investigation people, those, the geologist side of me, we were using discrete samples back from the mid-80s and then 90s. Never really made that connection that you need to do a statistical analysis to discrete sample data sets to make a call on whether an area was clean or not when you're looking for boundaries of contamination. But now we're skipping that stage, a lot of us, and jumping straight to multi-increment sample methods is a much easier way to implement this in the field. I think that's why we were just looking at individual samples in the past. We didn't have the money to go out and collect a lot of samples. We're trying to map extensive contamination. We didn't really have a method to do it faster and cheaper. Well, now we do. To point out, the Army Corps has been doing incremental samples or multi-increment samples for decades. So that gets to a point, then what are we looking for? We're not really worried about individual discrete samples and tiny masses of soil. And this, I'm not going to go over this in a lot of detail, but this concept of decision units is really nothing new. It's in our guidance. ITRC, ISM webinars do a good job of discussing this. The decision unit, the best way to think of it, it's the area and volume of soil that you would send to a lab as a single sample if you could, and they would grind up and test that entire sample. Of course, you can't do that, so you have to collect samples within that area, within that decision unit, and hope they're representative and have the lab test those. So we talk about source area or spilled area decision units where you suspect contamination may be present, either something someone dumped on the ground in this left-hand picture or maybe around a PCB or transformer, you suspect PCB contamination here. Small areas, suspect higher contamination. Risk assessors talk a lot about exposure areas. It might be your front yard or backyard. You want to estimate the mean concentration of a contaminant within that area. I mean, it's a big commercial site. We looked at the site before. The goal here is, from a risk standpoint, is estimate the mean concentration of PCBs or lead or whatever contaminant within that area. Estimate your risk to workers exposed to exposed soil. So they were talking about decision units back in the 90s again too. Here's a quote from 1991 data, Guidance for Data Usability and Risk Assessment. Historical information on production, discharge, storage of chemicals, etc., can be used to identify separate hot spot. They start calling spot areas, really large areas for characterization. So they're already thinking about this. A key point here is that the grid spacing they came up with, at the time that's all I knew was discrete samples, the grid spacing was designed so that they could identify these anticipated contaminated areas. A quote from 1987, to apply this grid-based discrete sampling method, the following assumptions are required. The shape and size of the contaminated zone must be known, or at least approximately known. And the second quote here is from Gilbert, who's referenced in most of the EPA guidance. When choosing a sampling plan, one must know the concentration patterns likely to be present at a site. This is exactly what we do when we go out to designate decision units. So an example is to divide a heterogeneous investigation area. So you know you've got more contamination in one area than another into more homogeneous parts for characterization. So that's a perfect example or perfect explanation of what we do when we go out to a site and designate decision units. So again, they were thinking about this 20, 30 years ago. Now, how big are these spots we're looking for? They call them hot spots. In reality, these aren't spots like the spot for a discrete sample. They're big areas. 1989 EPA guidance, Soil Sampling Quality Assurance User's Guide. So here they're saying if the particles of contaminants were all concentrated in soil so that they formed a hot spot of perhaps 10 centimeters of 1 acre, so their spot is 1 acre in size, it would be important to locate this 1 acre size spot so that remedial action could be taken. So if you're assuming spots 1 acre in size, then you space your grid for discrete samples 1 acre apart, because they're assuming any individual discrete sample within that 1 acre is going to identify the contamination and represent that entire area. This same quote in 1987 guidance EPA data quality objectives again. So the person setting the grid spacing must determine the acceptable probability of not finding an existing contaminated zone in the suspected area. You've heard this similar talk before, I'm sure. For instance, it might be determined that a 20% chance of missing a 100 by 100 foot, so 10,000 square foot contaminated zone, they're calling them. It's the hot spots, is acceptable. 5% chance for 40,000 square foot. But either way here, the point is, they're not, from a risk standpoint, you're not looking contaminant concentrations in individual discrete samples. You want the mean over very large areas, hundreds of square feet or thousands of square feet. That's always been the goal, even though from a field standpoint, we haven't been doing that. So that comes back to a point for risk assessments. Now, how do you know if the data set you get is representative or not? So in the same review EPA did in 1992, so 20 years ago or more, sampling data from Superfund sites have shown that data sets with 20 to 30 samples provide fairly consistent estimates of the mean. So they're saying up front, you need at least 20 or 30 discrete samples, or you need soil. Start thinking about it in this way. You need to collect soil from 20 to 30 areas within a targeted, or 20 to 30 points within a targeted area to estimate a mean concentration. So now we're starting to get somewhere. And this is where we hear a lot from risk assessors saying, hey, I need at least 20 to 30 samples before I can even start to come up with a reasonable mean. I haven't been able to find the original data for this report. If anybody has it, send it to me. So I'm guessing 20 or 30 samples, not bad. The default for multi-increment samples is 30 increments. So you have 30 points within the targeted area. That's what this is, one source of that. But we definitely see areas where 30 isn't enough. So let's go back. One thing we had for our study sites, each grid point in the study site, remember we had 15 separate measurements of the concentration of the contaminant in discrete samples. 10 from our intra-sample data, where we tested a single sample 10 times, plus 5 process samples around that grid point. Each one of these sites in each grid point, just looking at that intra-sample data, then we got 10 different choices, 10 different concentrations for each one of these grid points. So what we can do, one idea we'd had is let's randomly pick 10 different grid points, and then for each one of the study sites, and then randomly pick a discrete sample concentration for that specific grid point based on the range we estimate, or that we actually measured from our intra-sample data, and then estimate a mean concentration based on these random 10 points within each one of these study areas. So we're going to look at that data, random 10 points, see how useful those are. We also, each one of these grid points, let's assume, just look at all 24 grid points together instead of just 10 random ones. Each one of the 24 grid points, let's randomly pick a concentration of the contaminant for each one of those grid points based on the range we measured, and then estimate a mean using ProUCL for these. And let's see how compatible they are, see what kind of variability we see. So we ran 20 iterations of each one of these two scenarios, and we used ProUCL to calculate the means. Okay, let's see what we found here. This is each study site. Again, go to pick 10 grid points at total random. For each grid point, randomly pick a concentration for the contaminant, arsenic, lead, or PCBs. Estimate a mean. Here's what we found. For arsenic site, 20 iterations, 10 random points, we estimate a mean PCB concentration, that's the 95th% UCL, 403 to 776 milligrams per kilogram, just depending on which random set of samples we happen to select. It's about a twofold variability. One thing, look at the RSD. Once it gets over 35%, you start to question your data. The relative standard deviation range for each one of these random sets of data range from 34% to 67%. So starting to get questionable whether these 10 grid points, you can even use the data because there's so much variability. For the lead site, we saw a little bit more variability between the means we estimated based on 10 random discrete points within our study area. RSD, a little bit lower, but actually it gets higher also. So getting a much bigger spread in your variability and less certainty in how useful these data are. PCB site was interesting. 10 random points with PCB concentrations for each grid point. We calculated a 95th% UCLs for those 20 iterations. It ranged from 9.4 ppm to over 1 million ppm PCBs. So 10 random points at the PCB site, totally useless or unrepresentative. If you just went out and randomly collected 10 points, really you can't trust your data. Lead site, kind of mixed. Lead site, maybe the arsenic site, not that bad. But in general, we found the same thing EPA did back in the 1990s. 10 samples, you're just not going to get consistent reproducibility of estimated means. Here's the 24 grid point sample. So again, for each one of the grid points, we don't know if the 24 grid points are represented or not, but we randomly selected a data point for each one of the individual grid points based on the range we measured. So we had 24 points for each site, estimate a mean using ProCL, and we did that 20 times. For the arsenic site, 24 grid points, we're seeing a much tighter range and estimated 95th% UCL for arsenic, 395 to 492. It's actually pretty tight. Again, we don't know if the 24 points are representative, but we're getting fairly reproducible means. Again, though, the relative standard deviation, 39% to 54%, that's still kind of high. It's going to make a statistician a little bit nervous about how representative the data are. They're probably going to say, go out and collect a few more samples. You probably don't have the money to do that. The lead site, we saw a range in the lead concentrations, again, based on 20 iterations of random concentrations for each grid point, of 280 ppm to 394 ppm. RSD, again, relative standard deviation, see that same high variability. So we're not seeing that good of a correlation or reproducibility of estimated mean based on just by testing 24 random points within our lead study area. Still not that good. So 24 points, probably not quite enough. PCB side again testing PCBs, 24 discrete samples at each grid point. Do it 20 times. We see a range in 95% UCL, 652 to over 8,000 ppm. So that's 24 points within the PCB area. If you're trying to estimate a mean, then it's your relative standard deviation variability is way too high to make a call. And any statistician is going to call that out. They can't do anything with the data you sent them, even though you had 24 points. So we went back to each one of these sites. We also collected multi-increment data. So what's the real concentration, mean concentration of arsenic, lead, and PCBs at these sites? We collected 50 to 60 point increment multi-increment samples in triplicate. So we get a much more reliable estimate of the mean. Here's what we found for the study site A. We had really tight reproducibility of our triplicate samples. Again, 50 to 60 increments randomly spread out or systematic random within the area. 220, 250, 230 milligrams per kilogram arsenic for this area. RSD, 6.5%, which is super low. That means we're doing a really good job of collecting these samples. So very good precision. One thing I point out here is for people who aren't used to working in soils with very high iron, a few hundred ppm arsenic in this soil actually isn't that big of a risk because it's all tightly bound to the iron and it's not really bioavailable. The lead site, here's some multi-increment sample data for the lead site. Pretty tight concentrations, a little bit more variability, but 240, 270, 350 ppm lead within this area. Again, 50 to 60 increments. Our relative standard deviation, though, 20% is still below that 35%. So this is it's still a good data set. We can be fairly confident in the mean. We can calculate 95th percent UCLs from this. In this case, using student T's, 346 milligrams per kilogram. So just with 3 multi-increment samples at this site, we can say real clearly it's definitely above our action level of 200 milligrams per kilogram. We would make them do something at the site. It's below EPA's current action level, 400 ppm. So our MI samples are giving us good data. Site C, here's our replicate data here. Same thing, multi-increment samples. Here we had 60 increment samples. First sample came back 270 ppm PCBs. The second multi-increment sample came back 24, third one 19. So look at huge variability. So we did a pretty crappy job of collecting samples here, multi-increment samples. RSD, 138%, which is really, once you get over 100% especially, you can't really say much about the data. You know, there's a mean we estimate. We have to use the Chebyshev method for calculating 95th percent UCL, 467 ppm. You know, those numbers in the right ballpark. The mean concentration at true within this area is probably a few hundred ppm. But what we really need to do for this is split it up into smaller decision units and resample each one using a really high number of increments. We're saying now, based on our field experience, use at least 75 increments per sample. One thing our discrete sample data did tell us is that one area of the site's more contaminated than the other. So that's what you do when you go back. You split out that separate area that's more heavily contaminated, make it a separate decision unit, and resample it. And you should get much better data. Here's the comparison. So who's right? We got multi-increment data, discrete sample data for the site. Here's our discrete sample data summary here. Again, just looking at the 24 grid points. So just assume you collected 24 discrete samples at a site, each one of these sites. And we did it 20 separate times. At site A, with discrete samples, we saw a range in average arsenic concentration, 395 to 492. This is the 95% UCL. RSDs, 39 to 54%, kind of high, makes us a little nervous. For our multi-increment sample data, our triplicates, we got average 259 ppm, 95th% UCL. RSD, 6.5%. So the multi-increment sample data, much better, much higher confidence here. For the lead site, again, see this, fairly tight range, but within the lead concentration estimated, the RSD is 49 to 80%. That's still too high. It's going to make a risk assessor statistician a little bit nervous. They probably want more samples. 3 multi-increment samples, you get a mean 346 ppm. RSD, again, 20%, much lower. So again, much higher confidence here. Even the PCB site, the data were all over the place. We tested 24 random samples within that study area, and super high relative standard deviations. Can't really trust this data. With our multi-increment sample data, mean 467. Still, the RSD is kind of high. It is high, but at least we're getting closer. So with multi-increment sample data, we get much better precision. And also you have to think about sample support with our discrete samples. This last example we gave, we tested 24 discrete points within each one of the study areas. The total mass of soil represented by that was really 24 grams. Each one of those discrete samples, the lab tested 1 gram of soil. So very tiny. That's a large spoonful total for that whole area. 24 analysis. For the multi-increment sample data, we tested 180 points within each one of the areas. Total mass of soil represented several kilograms, much better sample support. We only tested 3 samples. So that's the key thing we're still wondering about here is how do you know when a set of discrete samples is representative of a target area? Statisticians can look at the relative standard deviation and make some calls on whether or not you need more samples, but even then, I'm not sure how you can do this. So just some notes here on, that's a kind of an ongoing topic. So the field representatives of a single data set, as far as I can understand it, really can't be directly evaluated. If you collect 20 discrete samples in a site, how can I know that's representative unless I go back and collect another 20 and compare the data and collect another 20? So you collect replicate sets of field data. No one's ever going to do this. It's too expensive. Also, any discrete samples have to meet sampling theory requirements for proper mass, distribution, shape, subsampling, and such. And that's something that isn't done. So it's a question to throw out to risk assessors listening. How do we know when a discrete sample data set is representative? So the last thing I end up with the risk assessments here is a quick discussion of outlier data, which is another one which just plagued environmental investigations. What do you do with these freak hotspots? So seek and ye shall find. Here's a note from 1989 guidance. Again, they were thinking about this back in the 80s, early 90s. The more discrete samples collected, the more likely one sample will exceed a cleanup standard. Well, yeah, that's exactly what we saw in our field study. The more points you hit, eventually you're going to start realizing the wider range of heterogeneity. So the more samples you collect, eventually you're going to start hitting these outliers that don't really match the other data. You start picking up nuggets of PCBs or something. Also, the smaller mass tested, the more likely that one sample will exceed a cleanup standard. If a lab tested 10 grams of soil from a discrete sample, they're going to get a much narrower range of concentrations than if they went back to that same sample and tested every gram of soil. And again, the maximum concentration of contaminant in soils eventually is always going to be above your screening level. If it's there, it's going to be 100% if you test a small enough mass. So these disruptive outliers, these have always plagued statisticians. And again, I worked as a risk assessor. I know lots of statisticians, and when we're doing risk assessment, we always get stuck with this uninterpretable data. Well, not always, but a lot of times. And putting my consultant hat back on, it's always a Wednesday, and they need the summary by Friday. And by the way, there's no more money to go and collect additional samples in the field. So that's always been a problem that's plagued risk assessors. And if you look at Pro-UCL's guide published by EPA, they're basically saying, if you want to give me this data with high variability with your discrete samples, high relative standard deviations, the only way I can make any sense out of it is just deleting the outliers, deleting these little hot spots you found with your discrete samples. So quoting from their document, outliers distort statistics of interest. From a purely statistical standpoint, therefore, it's desirable to not compute statistics by accommodating a few low probability outliers. That's purely from a statistical standpoint. It's really up to the field people to make a call on whether those outliers are representative of anything in the field or not, need to be thought about. But they were thinking about this again, too, in the 1980s. But here, the field people, I think the risk assessors versus statisticians are saying you keep the outlier data. Quote from the methods for evaluating the attainment of cleanup standards. Again, all data not known to be in error should be considered valid. High concentrations are of particular concern for their potential health and environmental impacts. I think as you're wandering back and forth across your backyard for 6 years or 30 years randomly, which is assumed in risk assessment, every now and then you're going to eat a small amount of soil from one of these little hot spots, and it contributes to your average daily dose, your average exposure over the year. In 2005, Pittard, so the godfather of sampling, was really hammering away at this. All the constituents of a lot or decision unit to be sampled must be given equal probability of being selected and preserved as part of a sample. Again, you need to find the outliers. You can't delete them. So really, the statisticians are being forced to fit their data into their models. And really, the outliers, it's not a problem with statistics. The outlier data for soil are really an artifact of improper sampling to begin with, or inadequate sampling. So to quote requote Pittard, 1993, when he was working with mining companies, especially improper soil protocol for particulate matter. Here we're talking about soils and particulate matter, introduces an enormous fundamental error into the data set that confuses the interpretation of the data. And that's definitely describes how we've been for several decades. And subsequent geostatistical studies. So you dump this data onto a statistician, and really they can't do that much with it without deleting outliers. Again, Pittard reemphasizing in 2009, a common error has been to reject outliers that cannot be made to fit a statistical model. The tendency has been made, again, to make the data fit a perceived model instead of searching for a more appropriate way to collect the samples. So here's the example for our PCB site here. Remember, at each one of these sites, we collected lots of discrete samples. We tested one sample multiple times. So here, I'm looking at the mean concentration of PCBs from our intra-sample data set for each one of these grid points. So I have a mean concentration of PCBs at each grid point, as if I just collected a single discrete sample there. And here's the frequency of concentrations within these the ranges here below. We had 6 of these discrete samples are below 1 ppm, 12 are between, 1.1 our action level and 50 ppm. 2, so you start to get these outliers that are greater than 50 to 250 ppm. Then you get these 4 samples within here, which I show with X's, that are greater than 250 ppm. So what do you do with these 4 bad outliers, which represent 17% of the site, really mess up a statistical estimate for a mean within a reasonable relative standard deviation. So what statisticians have been forced to do is pick these 20 good discrete samples and toss out the 4 bad samples. And here's what you get for this, just using the mean concentrations we estimated each one of these grid points. If you include the outliers, the 95th percent UCL concentration of PCBs for this area using the Chebyshev method is 1800 ppm, which is obviously very high, way higher than we really saw at any individual grid point. Look at your relative standard deviation, 328%, way above anything a statistician would consider usable data. So what you do, you toss out the outliers, and you get a much lower 95th percent UCL down to 41 ppm just by deleting these 4 samples. Your RSD is still high, but it's lower, so maybe statistician would be more confident with this data set making a call if it's legitimate to exclude these 4 bad outliers, which from a field perspective isn't, because we actually collected these samples and we know these areas here are much hotter. We also know that around any of these other individual grid points, if you just shifted over a little bit, you'd find another hot spot or big red X. So these 4 outliers are just representative of that area in general. You just happen to find 4 of them when there's lots of them. So gold miners that love outliers, putting on our geology hat again, they're looking for these veins of gold in little hot spots in their ore body. That's what makes it a deposit economic. So capturing and representing the distributional heterogeneity within a targeted volume of soil or rock, it's critical to correct sampling. The mining companies, again, have been doing this for decades. Outlier areas of concentration often drive decision-making on whether or not a deposit is economic or not, or even from a risk standpoint, whether it poses a risk or not. Here's why we never made the switch. I think from the environmental standpoint, from discrete sampling to multi-increment or incremental sampling, what the mining companies did is in mining, you dig up your entire DU and you grind it up and you extract it. And that's the ultimate test of sample representativeness right there. So they found out pretty quickly that their discrete data weren't representative of their deposits. And you go out of business really quickly if you do that. So that's why they made the switch to incremental sample, because it's much more reliable data for estimating mean concentrations within a targeted area. So again, it's the sampling method. It's not the statistical models that have been the problems. And you're always looking for the mean within a targeted area. So excavating these hot spots, you just throw this in. Another thing that's been real common but hasn't been really realistic at all is, here's another way to get rid of your hot spots in your outlier data. Instead of just deleting them statistically, then just go out to your site and dig up the soil around that grid point. Maybe even collect confirmation samples and find lower concentrations. You say, oh, okay, we took out our hot spots. Well, that's not realistic at all. Again, these are just artifacts of random heterogeneity within this area. And there's plenty more hot spots within this area. Here's our 20 iterations of random spots within the PCB area. And you can see they bounce around. You may take out these 2 hot spots here you found in the first data set. You go back and resample this set, the data, you're going to find these 2 other hot spots within there. And if you dig those out and resample, again, you're going to find other little hot spots, which you're just chasing your tail. So it's not legitimate to dig out individual grid points and then re-estimate a mean concentration by the remaining data. You have to resample the entire area to get a legitimate mean. Something to think about more later. Okay, so that's all these implications. I know you probably have your head is spinning now. And going back to the Matrix, I know what you're thinking. Cypher was in the same situation in the movie. So I know what you're thinking, because right now I'm thinking the same thing. Actually, I've been thinking it ever since I got here this morning. Why, oh, why didn't I take the blue pill? If you missed the first presentation, the blue pill means you don't have to think about the implications. You just run with what you've been doing. Well, it's a lot more fun to take the red pill in life. It keeps life a lot more interesting. So luckily, as we discussed before, really understanding the limitations and unreliability, a lot of cases, a discrete sample is pretty complicated. But the solution, luckily, is pretty simple. You just collect bigger samples. Here, quote another philosopher, Dr. Seuss. Sometimes the questions are complicated and the answers are easy. And it is, once you get out in the field, understanding decision units and the need to collect bigger samples, multi-increment samples, is pretty clear. And again, they were thinking about this back in the 90s. There's a guy, I forget who wrote this, but at the time, Petard is French. His original book was written in French. Someone in the EPA who understood French read his book. Here's a quote from it. "Particulate sampling theory is new to most environmental investigators." It's kind of funny. It still is today. Even though the techniques used to apply the theory to soil sampling are familiar. So they were thinking about sampling theory way back in the early 90s. They didn't know how to apply it, though, in reality. The main thing was they didn't understand risk. They didn't understand decision units. And they didn't understand how you designate decision units, exposure areas, and that you need to look at the mean concentration within a targeted area of soil. So the last thing, we're going to go through sampling theory, and the original quotes from the first presentation also, they were quoting Albert Einstein. We're going to spend, if we had an hour to discuss a problem, we're going to spend 59 minutes discussing the problem and 1 minute discussing the answer, and that's what we're going to do now. So sampling theory is lots of details. It can get really complicated. I'm still working on this after several years. You see all these are all different ways you can mess up collecting a sample. How you do it in the field, how big your sample is, how they extract it and subsample the lab, and on and on. We're not going to go through that. Here's a quick explanation of sampling theory explained with a salad. So let's say with a salad, your primary concern is long-term exposure to tomatoes. Maybe you're allergic to tomatoes for some reason. We're not worried about acute effects. Even in environmental work, we're always concerned about chronic effects. And we talked about that in the first session, and also we can talk about that later. So the wrong question to ask is, what's the maximum concentration of tomato in this salad? Or what is it? Here's a quick guess, hint, it's 100% if you happen to pick an individual tomato. Another wrong question, what's the concentration of tomato at point X? Well, that's not the question within the salad, because you're going to eat this salad over your lifetime. You want the mean concentration. Here's the right question in terms of sampling theory, is what is the mean concentration of tomato in this salad? If you could take this entire salad, send it to a laboratory, and they give you the mean concentration of tomato in it. So in this assessment, from a risk assessment standpoint, now we're starting to kind of marry risk assessors with the people doing the field work. Is what we're assuming is that random bits of salad are to be eaten over a lifetime. So the entire salad represents an exposure area decision unit. That's where you have to start, and we want to know what the mean concentration is. Well, how do you do that? You walk across the salad and grab handfuls of salad systematically, from a soil standpoint, from at least 30 to 75 points within that salad, and you put it in your bucket. And there's you're collecting a really big incremental sample, or multi-increment sample, as we call them here in Hawaii. So that's how you sample a salad. You don't just grab individual handfuls and test each one. They could be very different from point to point, and you're going to get lost. That's all a multi-increment sample is. A key thing, though, is you need to hit enough points within that salad, within your decision unit, to capture a represented number of hot spots and cold spots of tomatoes within that salad, so you end up with a representative sample. The sampling theory is simple in the end. You need to collect a big sample in order to capture and represent the random small-scale distributional heterogeneity within your targeted area. And the key thing is you want to capture the outliers. You want to capture those tomatoes. You don't toss them, because that's actually what you're looking for. And if you happen to grab a handful of salad with a lot of tomatoes in it, well, that's part of your decision. You don't throw that handful out, because then you've ruined your sample for the salad as a whole. For soil samples, you hit, again, 30 to 50 points within a decision, or even more for PCBs. Now we're saying 75. And typically you're collecting 30 to 50 gram increments. So a small handful of dirt each one of those points, you combine that into a big sample and collect a minimum 1 to 2 kilogram samples. So that's how you do, that's multi-increment sampling, pretty simple. A big step too that's never done but has to be done with multi-increment sample is lab processing. So if this was soil, the lab will get your sample and they're going to sieve it and dry it and take out the sticks and rocks we're not really concerned about. Just look at what people are exposed to. But then when they subsample it, they're not going to open the top of your salad container and just grab a tiny speck of salad. They have to open your salad, spread it out evenly, and then randomly go through it and pick 30 to 50 increments, the same thing you did in the field. Make a little small house salad, if you want to call it that, and that's what they're going to test for tomatoes again. So now the aliquot tested by the lab is represented the sample, and the sample is represented the field. So that's a sampling theory and multi-increment sampling explained in a salad. It's actually quite simple. Also, a key thing here is how do you know those points you collected in the first place, those handfuls you collected, 30 to 50 or 75, are representative? You're going to go back to your salad and collect 2 more samples. You can do it 3 times, completely independent from different areas. And my dots show the same areas. They're actually from totally different areas in the salad. You're going to test each one of your samples independently, compare the data at the end, and you're going to look at the variability of your data, the relative standard deviation. If it's less than 35%, good sample. Over 100%, you got big problems. You didn't sample your decision properly. So that's how you test the precision. This is not done in discrete sample data. If you think you've got more contamination up front in your salad area, then you split that off into individual decision unit. We call this a spill area decision unit. In Hawaii, ITRC calls it a source area decision unit. But if you think it's more contaminated, it's a critical thing. You split out your spill areas separately, test them independently. You still test on either side of your spill areas to confirm in your perimeter decision units that they're clean. So that's all sampling theory. If you want to know about it in detail, take Chuck Ramsey's 4-day class. Learn everything you need to know. You'll still have to think about it, for me, at least several years. ITRC gives a good overview of incremental sampling methodology, as they call it. Next series of webinars, 2 parts, is in November. Then our technical guidance manual we publish here in Hawaii really goes into how to implement multi-increment sampling and decision units in the field. We're going to update that and have draft updates posted by the end of the year based on all experience we've gained in the last 5 or 10 years. Tons of stuff in our guidance manual. We go over sampling theory, how to designate decision units, lots of examples, what multi-increment samples are, and limitations of discretes. We still use discretes for initial screening in the field to help designate to use. We had a section on common mistakes and problems in the field. That's really useful. And then we go through a lot of details on what tools to use in the field and what you do with VOCs or excavations, stockpiles, trenches, subsurface investigations, ecological investigations. That's all in there. The field part is really fun because once you understand this and get a picture of what's going on in the field, it's really fun now to go out in the field and investigate a site because it's real clear. We've always been doing decision units. Now we know how to collect better samples. So I end up here with the implications. I know I threw a lot at you, but something to think about for the next couple of years. Let's talk about regulatory hurdles to end up here. Here's a key thing. There's no specific regulatory prohibition against the use of multi-increment or incremental sampling methods that I know of. And innovation, improvement, and efficiency in site investigations is generally encouraged by state agencies and US EPA. So the current hurdles to using multi-increment sampling are mainly just due to a lack of awareness of discrete sample unreliability. That's why I went out and did our study. And a lack of experience with DU MIS methods in the field. You really need to get out in the field and see it. Once you see it, it's not that big of a deal. We were in a similar situation in Hawaii in the early 2000s. But again, we've been doing this for 10 years now. So real quick focus on TSCA. That's been one thing we're focusing on now is testing PCB contaminated sites under TSCA. Again, this is where some of the original discrete sampling guidance was developed specifically for PCB sites. And that was the big assumption too at the time, that PCB contaminations within a spill area, say around a transformer or something, where you could assume they're uniform, so any one sample would represent your spill area and such. Risk assessment guidance is being concurrently developed. There's a lot of confusion in the guidance, though, in the 80s about what to do with your sample data. What does the discrete sample concentration mean? Should we be comparing discrete samples to these risk-based screening levels another group is developing? Well, the answer to that is clearly no, versus comparing the mean concentration target exposure areas, which is yes. A key thing they said in 1985, way back when, again, 30 years ago, they knew what they were putting out was going to be changed in the future with more experience. they need to get something out quickly because they had thousands of PCB sites to look at. One thing they threw in there, though, was future changes in EPA policy may invalidate some of the discussions in this guidance. So, these guys, the people doing this weren't stupid, if you want to call it that. They knew that they just need to get something out. This is what they based their initial guidance on. It was based on their experience with industrial waste and such, where if you test industrial waste coming out of a pipe, it's going to be consistent day to day, or in a transformer, the oil will be consistent. So again, back to the PCB sites, the key thing again with grid spacing, the grid spacing originally, when you looked at, was meant to identify spill areas. They estimated an average area of spill areas around transformers. They came up with 250 square feet. So you space your grid points around so that you can capture any spill area that's 250 square feet, which I forget how many tens of feet that comes out for a grid area. So that's what they were thinking of, and that individual sample would represent that area. Again, 1987, any discrete sample is likely to recommend to identify this contamination within a contaminated area based on that single discrete sample. Again, their main assumption was to apply this grid-based discrete method. The size and shape of contaminated zone must be known at least approximately. So they were already talking about spill areas and using that assumed sizes to space their grids out with discrete samples, which is exactly what we do for decision units now. What they got wrong, if you want to put it that way, didn't understand in the past, what these discrete samples aren't really representing the area. So here's what they were assuming is, let's say this area here, and the middle central area here, we have these 4 blocks. We're pretty sure there used to be a transformer somewhere in this area, and we have some PCB contamination here. We don't really know where. We split the area up into 4 DUs based on what we're estimating the size of this spill area might have been. We're going to, under past guidance and under TSCA's default guidance, we collected a single discrete sample within each one of these, what we call them now decision units. And then they were calling them contaminated zones or sampling areas. We're assuming this discrete sample would identify the contamination and represent essentially the mean concentration of PCBs within that area. This is the default approach in TSCA regulations for self-implementing on-site cleanup. They include some default grid spacings in there. The basis for those is unclear, and they were getting really confused back then, or they were confused over what the meaning of any individual discrete size sample meant. Well, here's all we did now. What we're doing with multi-increment sampling is just the exact same approach. You split your area up into assumed spilled areas and maybe clean areas, and use that for investigations. But instead of collecting a single discrete sample within each one of these areas from a single point, we're collecting a really big multi-increment sample from multiple points within that targeted area. And that's a true sample. And we're much more confident in getting a representative concentration of PCBs within that area than we would be collecting a single discrete sample. That's really one of the key differences there with sampling. Instead of discrete samplings for individual areas, one sample, now we're moving to one multi-increment sample. And we'll also do triplicates. And also the samples now, when we send it to a lab, the lab has to process the samples and subsample them. So we actually get data that are representative of the sample, which can't be said for discrete samples. So how do you fit this in under TSCA? When you start thinking about this, a big issue in TSCA is dilution. And that's something we've had a lot of discussions with about some of the people in EPA. What exactly do they mean by dilution under TSCA? And really, when you think about it, go back to this figure here. Dilution is where you're combining soil from what should be independent decision unit areas. So let's say you anticipate this area to be clean. You think this might be contaminated. Dilution is when you combine soil from anticipated clean areas with an area that you assume up front or suspect could be contaminated. So that's a bad thing to do under TSCA. There's a very stringent anti-dilution clause that says no person may avoid any provision specifying a PCB concentration within a targeted area, within a spill area, as we call it, by diluting the PCBs unless otherwise provided. In the case of soil, that would mean combining soil outside the spill area. So this really, what it comes down to is it really requires careful designation of spill area or source area decision units when you're looking at a PCB site in coordination with the regulatory agency. So it's real critical, especially for PCBs and really anything, to identify suspect spill areas and characterize them separately. If you combine them with what you think could be clean areas, you're going to be violating this anti-dilution clause in TSCA. Now, another thing under TSCA, is they allowed composite samples, and they actually allowed diluting your sample that from a suspected spill area. Maybe you don't know where it is, you think it's somewhere in here, but they allow you to dilute the sample for that area by combining your discrete sample or multiple discrete samples from other areas into a composite sample and testing as one sample. So you've got this discrete sample from one of these suspect areas. You've got 4 here. Let's say I think PCB contaminated areas, it's in one of these 4 areas here. So I collect my discrete sample representing each one. I don't want to pay to test all 4 of them, so I combine it into a single composite sample, have the lab test it. So that's true dilution of spilled area, even if you don't know where it is. But one thing you have to do under TSCA, if you do this, if you do collect a composite sample, you have to divide your laboratory result for that composite sample by the number of samples you included in the composite, which makes sense. You want to make sure if there is a spill area in here, that area, the concentration of PCBs, the mean concentration there isn't above your cleanup level. So that makes sense there. But a key thing for multi-increment samples, think about is this single multi-increment sample here. Actually, so stepping back a minute, theoretical compositing multi-increment samples, I never even thought about this before I read TSCA, from separate DUs. In theory, these same 4 decision units, now instead of 4 discrete samples, let's collect a good multi-increment sample within each decision unit. I could combine all 4 of these multi-increment samples into a single composite sample, have the lab test that composite, and then divide the result by 4. And that would tell me what, within any individual area, I know that the highest concentration of PCBs would be 4 times what the lab reported for that composite sample. Well, that's an interesting idea. A key thing here, though, is this multi-increment sample is not a composite sample under TSCA. It's just a better sample of that targeted area. Instead of collecting soil from a single point, we collect the sample over multiple points within there to better represent it. So that's a key point I want to re-emphasize, is a single multi-increment sample collected from a single DU is not a composite sample. It only becomes a composite sample when you start crossing DU boundaries and combining soil across what otherwise should be separate individual decision units. Then you're making a composite sample. Point here, though, is composite samples or compositing of multi-increment sample is not allowed under HGOH guidance. So we've got the slide in here, but our office would never agree to letting consultants, or we have our own field team. We would never do this ourselves in the field. After spending all this time collecting good samples within our decision units, we would never combine the samples, mix them together, and make a composite and have the lab test it, even if they did process it. So 2 key points there is you want to avoid dilution at PCB sites by very careful designation of your spill areas and separate from suspect clean areas. And you're not allowed to composite samples under multi-increment sampling methods. A quick summary of that we just said. So now here's the improvements over the last 30 years. We have a much better understanding of what hot spots mean in terms of risk and decision units are. We talk about spill areas and risk-based exposure areas. So much clearer idea of that and what these risk-based screening levels apply to. They don't apply to individual tiny masses of soil tested by the lab. They apply to the mean of your targeted area. We also now know that a multi-increment sample rather than a discrete sample is required to characterize a targeted contaminated zone or sampling area. We call it now a decision unit area. Also, another improvement, and really with DU-MIS, we're just making improvements to TSCA. We collect replicate MI samples, test precision of that initial sample we collected. So it goes back to the point, how do you know 20 to 30 discrete samples was representative of an area? Really, I don't see how you can know that unless you go back and collect replicate samples, and that's required under our guidance and under multi-increment sampling methods. So ultimately, really all DU-MIS investigation methods do, they add greater upfront time and cost to an investigation, but ultimately they provide a much more reliable, faster, and cost-effective means to getting to an endpoint. So that's all that is. Right now we're still in discussions with people in EPA. They've been out to the field. We've done DU-MIS investigations at several PCB sites now just to get a better feel for it. And what we're proposing and working with them is under TSCA regulations. There's, again, the people that wrote the regulations knew this wasn't the Bible, this discrete sampling approach they included in there with grids and such. They included a clause in there called risk-based disposal approval. It says any person wishing to sample, clean up, or dispose of PCB contaminated remediation waste or contaminated soil in a manner other than prescribed in the self-implementing section that talked about discrete samples and grids, must apply in writing to the EPA regional administrator in that region. So that's what we're doing now. We're working with US EPA Region 9 and EPA headquarters to come up with a more formal agreement on using DU-MIS sample investigation methods at PCB sites that come under joint oversight between our office and EPA. So that was pretty long-winded. I hope you stuck with it, and it's something to think about more in the future. Again, if this is all new to you, just thinking about the limitations of discrete samples, if you got it in an hour, then you're a lot better than most of us. Just to quote the Dalai Lama talking about enlightenment, if someone tells me that they caught on to enlightenment over a very short time period, I wouldn't believe them. So same thing here. We've been thinking about this for years, and we're still thinking about it. But in summary, the concentrations of contaminants within and between co-located discrete soil samples can randomly vary by orders of magnitude over short distances. So that the result you get from a lab for a discrete soil sample for a grid point is completely random within some unidentified range of concentrations around that grid point. And this is totally predictable from sampling theory. And that's why a lot of people, I would say a lot, about 30% of the people that when they start reading the sampling theory and understand that, they immediately latch onto it. That's all you need is to understand the theory. People like me need to get out in the field and actually do it. So laboratory data for discrete samples are not reliably representative of the discrete sample provided. They're within some range of heterogeneity within that sample. Same thing, discrete samples collected in the field, they're not reliably representative of the area where they were collected, except within some unknown range or some narrow range. From our data, we're saying use an order of magnitude as a default if you need a default number. It could be way worse than that or even better. So this represents an unnecessary delays and added cost to site cleanup. And that's the key thing. Why do this? Maybe discrete samples is good enough. Well, it's really unfair to the RPs. It creates havoc in site investigations, especially on projects that are currently being developed. It can just shut down a site, and it creates a lot of brownfields. And DU-MIS approaches, they're specifically designed to address the deficiencies and improve reliability and efficiency of environmental investigations and compare it to discrete samples. So this whole idea, go back to it again, really this whole idea of multi-increment samples and discrete sampling theory and decisions and such, it's not another tool in a toolbox. That's a key thing to remember. It's a new toolbox. It's an entirely new and improved set of tools that we need to gradually transition to. And it's specifically designed to address the deficiencies that we had in our past experience with discrete samples. So I'm going to end there finally. I know that went on for quite a while. Hope you stuck with it. So any questions that come up, let Eric read through the question. I'm going to deal with this quote from Robert Pirsig. Eric, it's all yours.
All right. Well, thank you, Roger. Thank you to all our viewers who've hung on. I know that we've gone quite a bit over time. We really appreciate your interest. We actually didn't have anybody submitting any questions this time. If anybody does have any questions, there's a Q&A feature in this webinar, and please go ahead and submit a question, and we'll be happy to answer them. If not,
I guess in the meantime too, Eric, like I said, I've got my own questions.
Why don't you go through a couple of those then?
I'll start out with those. We covered one. If discrete samples are so unreliable, why didn't we figure this out 30 years ago like the mining industry did? I think the key point there is that in the mining industry, mineral exploration, they dig up their entire site and extract it. And they have to know very precisely what the concentration of gold is in an area before they mine it. So they had huge impetus to get the sample data right, where we don't do that in environmental work. We don't ultimately go back and dig up a PCB contaminated site and extract all the dirt and estimate PCB concentrations. So we didn't have that impetus, and we really didn't understand that there was an alternative to our existing approaches. And somebody asked before, is there any place for discrete samples? Well, yes, in our guides, we talk about using discrete sample data for initial screening of sites. And you shouldn't throw out any data you have for a site. But discrete sample data can be really useful helping designate the use. And another question that comes up, does this mean we have to go back and resample all the sites we closed over the last 30 years? Well, no, that's another thing we've realized in our investigations, right? We go back and resample sites that were initially investigated with discretes. you'll catch the core of the contamination with discrete samples, the heavy contamination. But the problem is that you start to really get confused when you get in these mixed areas where you have isolated hotspots and such to get really heterogeneous, and it drags out the investigations unnecessarily and runs up the cost. That's really the key point here is we're not making people go back and relook at sites we've already closed. But this makes the whole process much more efficient, time effective, and cost effective. And then the last question I was asking myself, why didn't we do this 10 years ago at Department of Health? And it's, that's a good question. And really there's two things that came up. One is we had a real good group of people we're working with who understand the theory perfectly. So for them, the theory was enough just to jump and go into the field and start doing it. Another key point, why did Hawaii jump on this 10 years ago when most other states haven't, is we have our own field team where we go out and investigate abandoned sites. So the theory part is one thing, I kind of got it, but once you get out into the field and see what's actually going on, it's totally clear. And it's not such a big deal designating decision units. We've been doing that for decades, but then actually collecting a multi-increment sample across some contaminated area instead of collecting a single discrete or even a few discrete samples. So that's the reasons that we've jumped on it and why we delayed doing this discrete sample field study like we did, looking at limitations in more detail. Is a good group of people already got the theory, and plus we already jumped ahead and we're doing this in the field and saw it's very useful.
All right, well, it looks like you've probably overwhelmed everybody, Roger, because I haven't seen any questions come in the door. And seeing that we've gone quite a bit over time, I think we probably should wrap up at this point. Thank you very much, everyone. We've still got several dozen people logged in and watching. That's great. Again, this has been the Hawaii Department of Health HERE webinar series, part 2 of our webinar on field investigation of discrete sample variability. This webinar has been recorded and will be posted on our HERE webinar series YouTube channel. You'll see that probably in a day or two. And all of our previous webinars are also posted there. Please feel free to go back and take a look. The PowerPoint for today will also be posted. And I think that that's about it. We have upcoming webinars. Nothing is currently actually scheduled on the calendar, but our plan is that in 2016, we will be doing webinars on the HERE office's technical guidance manual. We're going to be doing a section-by-section discussion of the TGM. Roger, did you want to add anything more to that?
No, we'll start off early on with going through section by section of our sampling methods, similar to what we did here. And I'd also say we're updating those now. We're making final kind of draft edits to our sampling sections to cover all the discussions we went through today. And you've got my email address up front. A lot of you have my phone number. So if you have any ideas, any comments on this, or something you want to see get put in the manual, our guidance manual, this next update, then give me a call or send a note, especially on the risk assessment side. That's what we're trying to improve, that section.
All right. Well, thank you, Roger. Thank you for all of our viewers. And this concludes the HERE webinar series presentation on discrete sample variability, part 2. Thank you, everyone. Aloha.
Okay, see you next year. Thanks.